Welcome. In this explainer, we're going to dive into one of the most fundamental equations in all of physics and mathematics. Seriously, it describes everything from your coffee cooling down to how information spreads across a network. It's called the heat equation.
I mean, have you ever really thought about it? You pull a piping hot pizza out of the oven, and what happens? Slowly but surely, that heat just spreads out, evening itself out until the whole thing is at room temperature. Well, that process, that diffusion, it's not random at all. It's actually governed by a really beautiful and surprisingly powerful piece of math.
So this is it. This is the star of our show today, the heat equation. At its heart, it's what we call a partial differential equation, which sounds complicated, I know, but all it's really doing is telling the story of how any kind of concentration, whether it's heat, a chemical, whatever, naturally smooths itself out over time.
Okay, let's not get intimidated by the symbols here. We can totally break this down. That part on the left, du over dt, that's actually pretty simple. It's just asking how fast is the temperature, U, changing over time, t. The right side, though, d squared u over dx squared, that's the really clever part. It's the second derivative with respect to position x, and it measures the curvature of the temperature. So imagine a really sharp, pointy peak of heat. That has high curvature, right? The equation tells us the temperature at that sharp peak is going to drop really, really fast. And K, that's just a number, a constant for the material that tells you how quickly it lets heat spread.
So you might be wondering, where does an equation like this even come from? It's not just pulled out of thin air. We're not going to get lost in a super formal proof here, but we can absolutely build up the intuition for it just by starting with a couple of really basic, common sense ideas about how the world works.
It all starts with a super simple idea: balance. If the temperature in one little spot changes, it has to be because heat either flowed in or flowed out. That's step one. Then, for step two, we have to describe that flow. And that's where Fourier's law comes in, which basically says that heat loves to move from hot to cold, and the bigger the temperature difference, the faster it moves. So, when you take these two physical ideas, balance and flow, and you express them using math, boom, you get the heat equation. It's really just a mathematical sentence describing a physical truth.
Okay, enough with the theory. Let's put this thing to work with our first example. What happens to a system when you just let it go? You let it sit for a really, really long time and let everything settle down. In physics, we call this the steady state.
So let's imagine you've got a metal rod. You're holding one end over a flame so it's hot, and the other end in a bucket of ice so it's cold. After all the initial weird fluctuations are over, what does the temperature along that rod actually look like?
Well, after a long enough time, things reach an equilibrium, right? The temperature at any given point on the rod just stops changing. It settles. So that means the rate of change with respect to time, our old friend del U del t, that term just becomes zero.
And if du dt is zero, our big, powerful heat equation suddenly gets way, way simpler. The whole left side vanishes. We're just left with this. The second derivative of temperature with respect to position is zero.
So, what kind of function has a second derivative that's equal to zero? Think back to your calculus class. Yep, it's a straight line. It's that simple. It means that after all that complex diffusion and settling, the temperature profile along the rod is just a perfect straight line, connecting the hot end to the cold end. How cool is that?
All right, for our next trick, let's play detective. You know, sometimes in a differential equations course, you're not asked to find the solution. You're just given a potential one and asked to check if it's legit. So let's put one to the test.
Okay, here's our suspect. This function, u of x comma t equals e to the minus t times sine of x. And just to make our lives easier, we'll pretend that our material constant k is just 1. The big question is, does this function actually satisfy the heat equation? Is it a real solution?
So, how do we check? We just need to plug it into both sides of the equation and see if they match. On the left side, we need the time derivative. That's pretty easy. It just gives us negative e to the negative t sine of x. For the right side, we need the second derivative with respect to position. Okay, so the first derivative of sine of x is cos x, and the second derivative is negative sine of x. So the right-hand side is also negative e to the negative t sine of x. They match perfectly. Case closed. This is a genuine solution.
Now this is my favorite part. Let's get away from the symbols for a second and just watch what this equation is describing. So imagine we have a long, cold rod, and we just zap it with a tiny burst of heat right in the middle.
At time equals 0, here's our starting point.
All of that energy is packed into one tiny little spot. It's a tall, narrow spike of very high temperature, and everywhere else is still cold.
But now, watch what happens as time starts to tick forward. The heat does what heat does. It starts to spread out. It diffuses from that hot spot into the colder areas next to it. You can see the peak is getting lower and the base is getting wider. The energy is spreading out.
And if we fast forward to time equals 10, the process is even clearer. That initial sharp spike is now just a low, wide, gentle curve. The energy has smoothed itself out across the rod. This picture, this animation right here, this is the very soul of the heat equation in action. It's that natural, unstoppable tendency towards equilibrium.
So let's just quickly recap the big ideas here. First, the heat equation is basically the fundamental law of diffusion. It explains how stuff spreads out. Second, it all comes down to that balance between the rate of change over time and the curvature or pointiness of the heat profile. We also saw how systems, when left alone, will often settle into a really simple, straight-line, steady state. And most of all, this equation is just a beautiful mathematical picture of the universe's tendency to smooth things out. And I want to leave you with one final thought, and it's a big one. You know, we've been calling it the heat equation this whole time, but it's really the diffusion equation. The exact same math describes how a drop of ink spreads in a glass of water, how a pollutant disperses in the atmosphere, and some economists would even say it models how financial risk spreads through a market. It makes you wonder, right? What other parts of our world are just following this same elegant mathematical rule?